Theorizing that there were new ways to transmit packets, Tim Zaghetti stepped into the quantum network and vanished. He found himself at Tech Field Day, facing delegates asking him questions, and driven by an unknown urge to teach them about quantum networking. And so he finds himself leaping from session to session, striving to teach right what was once taught wrong, and hoping that each time the next leap will be the leap home. It's all yours.
That's absolutely brilliant. What an introduction. It's like, and I can say they can top that. I might as well just, it's like a mic drop, and now it's like, it's over. Okay, very good. So I'm here to share what we're doing, what Cisco is doing in quantum. So I'm part of, I know many of you, and so for those that don't know me, I'm part of a group within Cisco called Outshift. It was formerly known as Emerging Technologies and Incubation. And what's different about our group, while every part of Cisco does research and development, you make existing products and portfolios better, our charter is to say, where else can we bring our thought leadership? Where else can we bring our innovation? What kind of emerging technologies, what kind of business problems of tomorrow should we start tackling today so our customers will have the solutions as they run into these? And so that's our overall charter. And so perhaps you've heard that there's been some innovations in AI. I don't know if you guys heard about any of these or Hypershield or anything. But on top of that, too, there's a few other things we're doing, such as, oh yeah, we're building a quantum internet. We're beginning to do this. It's really, really exciting. And just like we're taking leadership in building our what's now already being referred to as classical internet, which makes me laugh because if I hear classical, I think of something that's hundreds of years old or decades old, like a classical car or classical music. But it's the next generation, and like what is needed in order to bring this to a reality. And so I know we're not supposed to talk too much about why build them, but I do want to cover a couple really brief use cases, such as the most pressing and urgent one is quantum key distribution. If you haven't heard already, quantum computers are really fast, and with specific algorithms like Shor's algorithms, they present a real and imminent threat to asymmetric key exchanges, particularly any type of public key infrastructure, PKI. All the Diffie-Hellmans, all those elliptic curve variations, they're all at threat. And we did a session yesterday where I went through the math of how and why that's a threat. We're just going to, take it. Yeah, they're the threat. This is why there's the Y2K and the whole initiative set up by the White House in response to that threat, which is post-quantum cryptography through the National Institute of Standards and Technologies. So basically, your encryption is only as strong as your key exchange. If you use PKI, you're already at threat, and there's a lot of harvest now, decrypt later approaches happening. Whereas there's two ways around that. Either use PQC and those new cryptographic techniques for your key exchange, or quantum key distribution. We already see a lot of companies and even nation states. China has built out a huge QKD network as well. So those are the two main approaches. That's the most urgent use case. However, that's not going to be the dominant one. The dominant one will be distributed quantum networking. Basically, quantum computing is where digital computing was in the 60s. And so given that, we recognize that any computer, no matter how advanced, how powerful, is going to be that much more so as it's interconnected. And so there's so many opportunities, parallelism, and other benefits from interconnecting these quantum computers. That's what's really going to drive it. However, there's some additional ones too I want to call out. Network synchronization, and distributed sensing. You can achieve far more greater accuracy by interconnecting these sensors or clocks with quantum networks than you can with regular networks. It's actually called a quadratic improvement. And as such, for instance, if I had a radio telescope array looking out into deep space, right, my classical precision could be improved by a factor of 1 plus or minus 1 over the square root of n, which is the number of these telescopes. So without touching the hardware itself, I can see deeper into space or farther back into time just by using a quantum network. Some really cool examples. Anyways, but in order to explain and give a little context with what we're doing, I'm going to have to just take a half step back and review some key concepts in quantum mechanics. And then very, very briefly, I know I'm short on time. I'm talking as fast as I can. And then we'll get into how quantum networking works And it's quantum networking. Like our near-term strategic goal is to build a quantum networking switch based on teleportation. That sounds really cool, huh? We're going to show how that works and what we've already been doing and what we're currently doing. Okay, that's my goal for the next 20 minutes. Okay, I don't think I had that. I haven't been. Okay, I'm like, I don't think I've been talking for 10 full minutes according to that clock.
But you're talking about quantum networking, so the clock shouldn't matter.
Awesome. It's funny too. I was called to do a briefing on this on the first day of April, and I started talking kind of like Tom. I'm like, yeah, I'm going to talk about quantum teleportation and how this will enable us all to go back in time and this and that. And people didn't respond. And I go, does anyone not see a correlation between what I'm saying and what day it is? You know, it was April Fool's Day, so you can have a little fun with that. Anyways, if somebody could just look into this, clicker's not working, but
you got to plug it in.
oh, layer one problem.
Yeah, that's not.
Is there an engineer in the room? Anyone?
That's not quite quantum yet.
Not quite? Okay. Okay, great. So that's what it is. I thought it was all part of the hub. Okay, so quantum mechanics, also known as quantum physics, basically it's a world of physics that are looking at behavior at an atomic level or less, smaller. So all the physics that Newtonian physics, classical physics, the three principles of, Newton's three laws, that all applies to things that are larger than an atom. Once you get smaller to that scale, all the rules just go out the window. And there's these seeming paradoxes. For instance, particularly a dual nature of these subatomic particles, where they exhibit characteristics and attributes consistent with particles while simultaneously existing characteristics of a wave. So how can you be a particle and a wave at the same time? It's very difficult to express. That's why there's a whole new field of physics. So to represent information, we have to find a way of representing a logical 0 or 1 with some of their attributes. And depending on the modality, that is how we represent a qubit, we can use electrons, photons, trapped ions is another method that's used. We look at different things. For example, for electrons, it's often termed as electron spin. But I do want to be clear, electrons don't actually spin. There's ways to prove that. They're basically a singularity, and as such, they don't fit the physical definition of spin. Plus, they do generate an electric field, and that can be generated by spin, but in order to generate that size of electric field that they discharge, they'd actually have to be spinning faster than light. So they don't spin, but I will use a visual aid of some tennis balls just to illustrate the concept of spin. I just want to be clear, it's not to be taken literally. It's just an analogy. So basically, electron spin, you take an electron, the fields, north-south, going from the top, the North Pole to the South Pole, that would be a state of 0. So when we say that, a state of 0, the electric fields come out of the North Pole towards the south. State of 1, they reverse. And incidentally, it's not just electrons that reverse their polarity like that sometimes. Even our planet Earth, on average, according to NASA, every 300,000 years reverses polarity. And it's varied. It's not consistent. The sun is more consistent. So it's every 11 years, and it's going to reverse polarity this year. But basically, that's one way that we can represent a logical 0 or a logical 1. And then this is very facilitated to the use of electrons for qubits is very conducive in the compute environment. But to maintain these states, they have to be in a very supercooled, very completely shielded from EMI, noise, vibration, temperature, everything, in order to maintain and to be able to measure and to manipulate these spins. However, because we're talking in networking and communication, we're actually going to be focusing on photons to represent qubits. And for photons to represent qubits, we're actually going to look at their polarity, so how they're vibrating and oscillating in the planes of propagation. Now, regardless of how we represent qubits, there's 3 key properties that we have to understand in order to understand how to manipulate them and achieve these results, like quantum teleportation, for example. And the first is superposition. So sometimes you might read about this, and when they say in some articles, oh, qubits represent 0 and 1 at the same time, it's very difficult to wrap our heads around, and I don't even think that that's a very accurate description. It's much more accurate to say that it's These qubits represent probabilities of 0 and 1 simultaneously. For example, take a coin, right? Is it heads? Is it tails? As it's in the air flipping, is it heads? Is it tails? Well, at any given instant in time, it has a probability of resolving to heads or resolving to tail, and that number, that probability is constantly, instantly changing until I finally take a reading, and then it collapses that superposition state of a probability of X, a probability of heads, probability of tails. Now it's collapsed to a single discrete value. I take that reading. It's very similar with superpositions of qubits. As they're in this state, they have a probability of being both, and so calculations can also be made on both values simultaneously. But ultimately, when we measure them, they collapse into a discrete state, and then they lose this special phenomena of superposition. So far, so good? Okay, now the next key cool thing, that's one of the coolest things in the universe, I think, is this idea of entanglement. And Einstein first noticed this in 1935, if you'd believe it, that long ago. And so he noticed that certain particles could enter a bizarre relationship such that a change in one is instantaneously reflected in a change in the other simultaneously, regardless of how far apart they were. He incorrectly concluded there must be something we're missing. We're not able to measure something. There's something that's local and real that we're just not able to get our hands on and identify. We just lack the technology that's accounting for this phenomenon, because ultimately nothing can move faster than light. And if there's a change in state that's somehow communicated between these particles that could be distances apart, galaxies apart, it just didn't fit. It didn't fit his overall thinking and theories. However, in the 60s, there was a Northern Irish mathematician, John Stuart Bell, and then he came up with a theorem called Bell's inequality to prove, theoretically to prove, that this was not the case, that Einstein was wrong. There was actually some quantum action going on. This was a nature of quantum particles to be able to reflect a change of state instantaneously. And it was very, very difficult to prove who was right. And it was only in 2022, that's just 2 years ago, that a group of scientists were awarded the Nobel Prize for experimentally proving that Bell's view was right, that quantum entanglement is actually a real nature of these quantum particles. You can entangle and multiple bits, not just 2. Current record is 54, and that's important too. We're going to come back to that in our networking. When you measure it, just like superposition, it all falls apart. It's like grabbing that coin, taking the reading. It's no longer got that interesting dynamics property, either of superposition or of entanglement. It collapses to a single state. And then depending on how it's entangled, the other will either be the same state, let's say spin up, or spin down. One, it could be like a mirror reflection of the other, or there's 2 other variations. These 4 states are called the Bell states. We're going to come back to that. Okay, another and third and final, not final, but third interesting property about qubits that I want to cover is no cloning. So it's mathematically, it can be proven that it's impossible to clone information that's encoded in a quantum state. The simple descriptive proof is that you can't copy something without first reading it. And if we said that we take a reading, well then that state, we take an instantaneous reading, but we can't copy and then eavesdrop and propagate it. It's done. That operation is a finish, it's complete, and there's no way we can eavesdrop and be undetected. And neither can we copy information in this state for our own purposes. I know this group is super technical. I'm not sure if is there an appetite for math? Because we can prove this if we want. We got this slide, and then there's a hardcore mathematics slide. Yeah. Does anyone want me to go through that? Because we can do that too if we have 2-3 minutes. Okay. If not, it's covered in the breakout session on Intro to Quantum Mechanics, Computing, Networking, etc. So, okay, with those 3 key properties in mind, superposition, entanglement, and no cloning, how do we bring this together and start building quantum networks? Okay? So, we're going to use photons as qubits. And the reason we're doing this is while electrons are commonly more used in computing environment, you see these quantum computers, they're all using electrons, but this in order to maintain their state, they have to be supercooled, minus 273 degrees Celsius. And if you had to keep your entire network, every part of your network supercooled, including the media, it'd be prohibitive to use electrons for communication, quantum communication. You have to use another modality. So we're going to use photons to represent our qubits. And so they're more conducive to the networking use case. And so when we talk about photons, we're talking and we're looking and measuring their polarization. So polarization is basically a plane of propagation that's perpendicular to how oscillations are happening. So I drop a drop of water in a nice still pond, and then you see the rings going out. The waves are going out, and the plane of polarization is horizontal. Does that make sense? But because obviously water is bound by gravity, you can only have the horizontal plane. With light, you don't have these kind of restrictions. You can polarize in an infinite degrees, infinite within the 360 degrees or even sub-degrees. And then we can measure the polarization using polarization filters. This is, probably some of us might even have polarized glasses here, or sunglasses or optical lenses. Right now I have two optical lenses illustrating down here. They're both vertically polarized. If I turn one of them a little bit, less and less light will go through until no light goes through. If they're perpendicular to each other, then theoretically no light will enter. There's a really cool tool on Olympus that allows you to play with these angles and illustrate that same effect. But basically that's what we're looking at. That's what we're measuring. And in quantum networks, we're measuring not just whether something is horizontally polarized as a 0 and vertically polarized as a 1, but we're also going to take a look at diagonal polarization. So a 45-degree angle, think of a /0, 135-degree angle, think of a \1. So we got four different options for four different options of polarization, and that makes it even more tamper-resistant. Well, tamper-proof, actually. Anyway, so now let's think about how we communicate classically. When we send fiber, information over fiber, optics over fiber, we're sending a burst of protons. And I don't know if you noticed, but not all of them make it. Okay, some of those are just attenuated over the media. It's just loss. And that's normal, but we send so many that there's enough that are received to give us a positive 0 or a 1 value. But the challenge here is that if we want to maintain confidentiality and just send a single photon, then you don't want to send multiple copies of your photon, because then somebody could eavesdrop and read the information and you'd never know. But you just want to send one qubit, and so you're really now limiting the success factor of getting that single photon over, and you don't want to just keep losing the data along the way. So that's a big challenge, especially considering that this rate of decay increases exponentially according to distance. Then perhaps you might think, okay, well, why don't we just boost the signal? Why don't we just do some amplification? And the gating factor there is this no cloning theorem. We can't read that qubit and then regenerate it and propagate it, because since in the instant we read it, we collapse that state and it's no longer useful to the receiver as a qubit. So they can continue operation, computing, or whatever else they want to use it for at the far end. So we have to figure out another way. So what is that other way? This is where this cool science fiction type of terminology has entered the picture. Quantum teleportation. So how do we actually, and this is based on entangling or entanglement of the photons. So how do we entangle photons? Which is different from electrons, but let's just focus on photons in today's discussion. We basically use this process which got a funny long name, spontaneous parametric down conversion. But really what it amounts to, I'm just blasting a powerful laser through a very specific type of crystal. It's called a nonlinear crystal. I start with a big high energy photon, and it splits it into two photons of lower energy. And this is what it looks like in an optical table. This is the crystal right down here. And so it's pretty straightforward to do, and it can be done at room temperature. So I how do I go about then communicating via teleportation? So Alice here, she starts with an entangled qubit using photons. We'll call that qubit Q. In order to begin the process, she actually needs to establish a teleportation channel. To do that, we grab 2 more photons and entangle them. They're absolutely unrelated and have nothing to do with Alice's photon that she wants to transmit. And we just entangle these 2 because this is going to be our channel. We hold on to one of them, A, and then we send the other one across the media to Bob. Okay? But now there's there's a channel, a teleportation channel. It's not a physical channel. It doesn't matter what media is in between. You could actually cut that fiber at this point and the quantum effect would still be in place, but we actually still need it because there's some more work that we need to have done. Now, the next step is actually encoding the data. So she does an entanglement operation. Remember, we said we can entangle more than one pair of photons. And so we're now entangling the one that's got the data with this random one that we're just using as a channel. Now, because of their states, which are uncertain, we don't know. We've taken signal and we've collided it with some noise. And so we have signal and noise at this point, if you'll permit me the analogy. I know we're not dealing with analog, but it's just perhaps a way to think of it. But what's interesting is that instantly, Bob on the other end has the same signal and same noise. Okay? So all we have to do now is remove that noise. To do that, we do a measurement on the near end that's called a Bell state measurement. As we mentioned, there are 4 possible states in how the electrons were entangled, and it's impossible to know in advance which state, because it's impossible to know the positions at any instant in time. But basically, we do an indirect measurement. We're not looking to read the qubit. We're just saying, hey, how are the polarities related? And that's all we're measuring. And so the superposition is maintained on the far qubit, but the 2 local qubits, we've broken the entanglement and we've lost that superposition of qubit A. That's okay, we don't need it. It served its purpose. Now, at the far end is still signal and noise, but now we know how to remove the noise. So with the outcome of our Bell state measurement, we know one of 4 Bell states that had occurred during the moment, the instant of entanglement, and then we just represent the measurement result as a binary value, a 2-digit binary value, and then we send that 2-digit binary value over classical media, fiber, or it could be just over satellite, to the receiver. Now the receiver knows what has to be done to restore and to remove that noise, to restore to the original state. Either he has to do nothing at all, or maybe a rotation around one of 3 axes. So x-axis, which is basically, if you think about an xy plane, basically the x-axis, you take an xy plane on paper, and if you just laid it flat through the center of the tennis ball, xy is going laterally, left to right through the tennis ball. And so lateral rotation would be from, if this was 0, and I rotate it down laterally, it would be a knot operation. It would be equivalent to the digital NOT gate. Or I might rotate around the y-axis. The y-axis would be front dead center to back dead center. I could do a rotation, but that's not relevant here, because effectively, if I start at 0 and do a y rotation, it's a knot operation again. So it doesn't matter if I use x to do the knot or y to do the knot, I get to the same result, top to bottom. And so it doesn't matter. Or I could rotate around the z-axis, which is top to bottom, and I do a rotation like that, or a diagonal rotation, x and z at the same time. It doesn't matter, that's a little extra detail, but basically I have to do one of these operations to restore the qubit to its original state. And now further computations can be made on it, or whatever else the receiver wants to do with it, they can, because it's exactly the same as it was sent. So this is the steps to quantum teleportation. It's pretty cool, but we're doing it in the labs already, and this is our near-term goal, like I say, to build a switch, quantum switch, based on teleportation. But that was over only one link. What if, of course, we're going to have multiple links? In which case, what do? We have to do this link by link. And then on the intermediate interconnection nodes, we actually do an operation called entanglement swapping. We kind of make an entanglement chain from all the way from sender to the receiver. And then when the chain's in place, then we're ready to go. And so here's what it would look like. No matter how many intermediate nodes, I do link by link entanglement. And then I do entanglement swapping across the device, the intermediate devices. And then now I have an end-to-end path. Now, those of you, I know some of you have been around networking long enough. This might look familiar to you. It's very, very analogous to switch virtual circuits, SVCs, ATM. If you remember those days, it's like, let's go back to CCIE days or what have you. And so it's interesting that a lot of concepts, that have been around come back around. But basically, we're making a switch virtual circuit. If there's a network failure event, no problem. We just reconverge. We reestablish these linked entanglements and then the end-to-end entanglement, and then we keep on going. Now, it's important to note, we have to do this operation for every single qubit we transfer. However, that is offset by the fact that qubits have a property that they can represent multiple values at the same time, 0 and 1. So the more qubits that you have to transfer, you're actually sending much larger amounts of data with far fewer qubits than you would regular bits. So for instance, if you had 1 qubit to transfer, you transfer to the equivalent of 2 binary values for computation. If you had 2 qubits to transfer, you're actually transmitting 4 binary values, the equivalent information of 4 binary values. 8, 3 qubits, 8, and so on and so forth. So exponentially, this works out in the favor of quantum computing, even though at a qubit by qubit level, there is all this steps to take and to implement for every single qubit. There's a tremendous number of challenges, top to bottom of the OSI layer. A lot of them have to do with maintaining state, maintaining what is called coherence, quantum coherence, reducing noise, improving fidelity, etc. These are protocol-oriented challenges, but even hardware has challenges. Like, how do you, if you think about in a memory, in a switch, the key role of even something is memory. We take that for granted. We have memory that is flash memory even, that we never think about. It's persistent as long as we want it to be. And we never have to think about, hey, what happens if, the memory forgets the given state? But with quantum technologies, you can only maintain memory for a very short amount of time. For instance, with photons, they actually use these engineered diamonds. Like there's a subsidiary of De Beers, the diamond jewelry company, and they manufacture engineered diamonds that have a special property called nitrogen vacancy, for example. And then these can store the quantum states of photons, originally just a few milliseconds, but a few years ago, they got it all the way up to 75 seconds. Well, that's fantastic. That's great. It's a huge leap forward. But still, if you're only able to store things in memory for 75 seconds, you have a lot of constraints to work with. And other types of modalities, you'll have even less time that you can actually store memory. So that's a huge hardware oriented issue as well. Okay, so then there's a number of issues that not just Cisco, but the industry is challenged with in order to deliver quantum computing and quantum networking. Here's just a summary. This is by no means an exhaustive list. We're focusing we're playing to our strengths. We're focusing on the networking requirements. So what is Cisco doing? This is what I want to share ultimately. There's 3 main steps that we need to follow. First of all, doing the research, the math, figuring out a blueprint. It's like, how can we even make all of this real and achieve the results we want? What is the scientific basis for it? And we actually have quantum research scientists on staff. It's part of our group in Outshift. And they're tackling these, and they're publishing groundbreaking research. On top of that, we want to do quantum simulation because it's very time-consuming and expensive to set up these optical tables and to do these experiments. And so you really want to make sure you maximize your bang for the buck. But then ultimately, as Einstein himself said, it's like, hey, in theory and practice are the same. There's no substitute for testing. And that's an important part of the hardware and software development. And so to do that, we've actually spun up our own dedicated quantum lab. Okay, so breaking them down according to these 3 steps, we published an important paper on how we could unify quantum, and you notice the term classical internet already. That's how it's being referred to. And so this is the overall master blueprint of how to bring this together. Further important papers were how that we can maximize the current infrastructure so that we don't require rip and replace mandate in order to support quantum in the near future, but maximize the utility of what's already available, minimizing the hardware investments. So if there's all these high-grade fiber optics, can we leverage these as they are? And if so, then how and what would that mean? How would that look like? Solving that. Now, we mentioned that electrons are typically more conducive to computing scenarios than photons, but electrons need to be kept at a supercooled state. Well, could you imagine, again, supercooling all your network gear, every place that you had to propagate something? That would be very difficult to do. So then we've done a lot of research and prototyping in how we could use photonics for computing, because there is computing requirements in networking devices, obviously. And so how can we achieve that using the modality that's optimized for quantum communication? Okay. And the next, we also then, if maybe some of you might be familiar with, IBM has a quantum circuit simulator, and it's really cool. So like if you want to learn about quantum gates and how to program a quantum circuit, they teach you about the different gates, and then you can go, and then when you compile your circuit, it actually runs it and executes it on a quantum computer and gives you the results, which is really cool. We've taken a page out of that book, and we've already developed a quantum network design kit, or a quantum network simulator. In fact, we had a technical breakout session on this earlier today, where we featured it, so that you can start playing with these protocols and start interconnecting and building quantum networks, getting a really good sense of how to expect them to perform prior to going and modeling and building out the hardware to make it real. However, ultimately, there's no substitute for hardware, which is why we opened our quantum research lab. Actually, I had spoken with Paul, and we wanted to arrange a tour for him of this lab prior to Cisco Live, but we were unable to do so because I didn't think I closed the loop with you on this yet, Paul, but when the city of Santa Monica found out, or realized the power of some of the lasers that we were planning on bringing in there, there was a lot of flipping out, and a lot of extra permits were placed on us, and so this was delayed by many months. But it's all good and all open, and I will arrange that with you at some convenient time. We've also done work on quantum repeaters. Now, when we're talking about quantum transport, I had made the point that you can't amplify when you're transporting, but that's not strictly speaking true, because there's a way to work around that. And the workaround is that instead of representing a qubit as with a single photon, we can actually represent the logical state of a qubit over many. So this was first proposed by a professor at MIT named Peter Shor, who also invented the Shor's algorithm, which is providing the biggest threat to PKI, the exponential speed up and cracking PKI. And basically he's saying you can represent the logical state over 9 particles of a single qubit. And that way, if you do lose something along the way, you can do a parity check, and then you can restore that loss and keep propagating it without actually taking a reading of the logical value of the qubit. So it's like a workaround. So that's really interesting approach as well. And that way we get around, we're not violating this no cloning theorem. And then finally, to come to my toy, right now we recognize that we need random numbers for many use cases. Cryptography, particularly so. You want truly random numbers. Any type of patterns are like the enemy that you want to fight against, because then once there's patterns, it's kind of like getting a little lever for a hacker to break that. But you want purely random numbers, but current digital algorithms are actually not random. They're pseudo-random. They take a mathematical seed, and then they take a specific seed and perform some mathematical operation in order to produce a string of numbers, but it's not truly random. Whereas reading quantum states is guaranteed and proven mathematically random. And in fact, it's not only a purely random number generator, but it has the verification capabilities using the same Bell's inequality theorem to prove that every component is maintaining true randomness. So it's some really new capabilities of the hardware that we actually have right here. You can see it's not very large, about 2 RU, runs on 120 volts, stack and rack. And we not only have this as hardware available, but also through the quantum network design kit. So if you want to get a random number, you just go onto that portal and you can grab one and continue and work away. So not just hardware, but that software. So in conclusion, we have a number of use cases driving quantum networks, most urgently quantum key distribution, but the really big one will be distributed quantum computing. Special properties of qubits, we talked about superposition, entanglement, no cloning. Teleportation, it's a multi-step process where we entangle a pair of photons, send one to our receiver, then we do a second entanglement, and then a Bell state measurement, send the result, and then make the correction based on that result. What is Cisco doing in quantum? We're doing research, we're doing simulation, we're doing hardware and software development. It's very, very exciting. So we're really glad to have this opportunity to share what we're doing, and there's going to be a lot more to come. So thanks for this opportunity, Tom and Gestalt, and all of you too. So I really appreciate it.
So Tim, on slide 1.
Yes.
So joking aside, so customers using it. What do we have for customers using it?
Our customers using it. So right now, this is what we built. It's a process. Like, we haven't built and delivered the switch yet. I'm just saying that that's our near-term strategic area of focus. However, this is available for customer consumption. Like I said, either probably the best portal would be through the Quantum Network Development Kit, and then they get a truly random and verifiably random number for whatever use case they have, typically cryptography, search generation, maybe simulation. But that's, that plus the research in the paper also helps not just us, but the industry, the various papers in general, allows them to not have to repeat the wheel. And so we do have a lot of publishing because we recognize that, hey, we'll all get there faster if there's good cooperation. And like I say, it's very exciting. If you think of where what regular computing was in the 60s, before people even thought of an internetwork, before Al Gore came to our rescue and invented the internet, they weren't really thinking of networking, but we're already thinking that because we've seen the evolution, we've seen the benefits. There's probably so many use cases we haven't realized yet. And so it's just tremendously exciting to be a little bit ahead of the curve, and we expect then the development to go that much faster for our prior experience and knowledge with digital compute and networking.
Just to be clear, using this for encryption key distribution, you'd be distributing symmetric keys to verify receipt of the key, but also verify that it wasn't eavesdropped along the way, because if it was eavesdropped, then the entire superposition would collapse upon arrival, right?
Yeah, so if it was eavesdropped using quantum key distribution, like there's two methods. With quantum key distribution, you would recognize right away because they wouldn't know the polarization, whether you used horizontal, vertical, diagonal, or anti-diagonal when you encoded a 1 or a 0. And they would have to guess. They would have to pick their filter in advance, and they would have a 1 in 4 chance of being right per chance. And then they would ruin superposition, and then that would be detected at the far end. And so the receiver and the sender would recognize then that there's been somebody eavesdropping, and then they just send some more. Do you know what I mean? So that's with QKD. With quantum teleportation, there's nothing to even tap into. There's no real media of that important communication. All you're doing is you're sending a blank particle over the classical channel, and then 2 digits of your measurement result over the classical channel. That they could eavesdrop, but it has no meaning to them because they don't have access to the actual qubit that's on the other side to remove that noise from the signal.
So that's what I was curious, like that bit about the teleportation you were like explaining. So the quantum's like, how it looks like, how physically this is being done. And then also you said that, you need to have a dedicated, almost standard network to transfer the zeros and ones, right? So how I didn't understand that bit.
Okay.
Well, I didn't understand more bit.
You know what? That's very common.
That's the bigger one I didn't understand.
Yeah. First of all, I just want to say in this field, a lot of these concepts are new. And they're new to all of us, including myself. And sometimes they take a lot of iteration and correction. And I got so many things wrong and banging my head against walls for so long, and our quantum scientists have been very patient with me. And, but anyways, long story short, you did latch onto something very important that I didn't explicitly cover, is that for quantum networking to happen, you actually need a classical network. There's never going to be this rip and replace.
Okay, so
you have a dependency, you have a mathematical dependency on some methods of classical communication. And actually that's something, so basically it will be a hybrid network.
Right.
It won't be fully quantum. It'll be a hybrid, quantum and classical. And you'll see that pattern over and over again, even with quantum computing. The entire quantum computers aren't quantum. There's elements of it that are quantum, but then the final measurements and readings are all digital processes.
Okay.
So it's a hybrid computer, to be more accurate. And so hybrid computing, hybrid networking, that's what's going to happen.
That makes much more sense now, because I sort of saw it as in a vacuum, completely outside of what do we have these days.
Yeah.
But it's actually hybrid, right?
That's it. That's it.
Okay.